Welcome back. All right, so independent events in probability, and most of the things that you do probably will end up having independence within them. So as you do more than just one event, you might see that you're going to have to be calculating probabilities and combining them together. So if you have multiple events, so you're kind of compounding events, so you have more than one. So compounding just means that you have more than one of the events. And when we say the events are independent, what we're saying is that the probability of one event that you're interested in is not actually impacted by an occurrence of another event at all. So if that is the case, then you can just simply take the probability of that event and go along with it. So I just want to show you examples where this happens. And then I have done quite a lot of different examples with regards to probabilities. Okay, so you're going to be able to take a look at those. I'll put up a link up to the playlist and you'll see a ton of examples within there. So here's one thing to think about this independence. When you're flipping a coin and it has, let's say, been flipped 3 times, right? And it's resulted in heads, heads, and heads, just as it says there. And then you ask the question, okay, so what is the probability of flipping a heads on the next try? Now, if you just started and you started to think about this and you said, okay, well, if I haven't done any flips at all, and I know that flipping heads is just simply 50% chance, right? Or 1 in 2 because you have heads and tail, assuming we have a fair coin. And if you wanted to do this on 4 occasions, so let's say, you were going to flip this 4 times. We can do a tree diagram as well to see all the occurrences. But let's say you wanted to get heads, 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 and heads. Then in this particular case, you would have a half, okay, a half, a half, and a half. Every single flip that you do is actually independent of any other flip, right? So just because you have flipped the heads on the first one, it doesn't mean that your probability changes on the second flip that you will do. So it actually does not matter at all how many heads we have flipped in a row. The next try that we do is still going to have a 50% chance of being a heads, because past occurrences, okay, do not have an impact on the future occurrences. So that makes the past events, okay, independent of the future events. So to answer this question, this last particular try right here, okay, the answer would have been just 1/2 or 50% chance in terms of the probability that you would have. Now, if you started right from the beginning and you didn't do any flips at all, and you wanted to ask somebody, what's the probability of seeing 4 heads in a row, okay, on the flips, then that's a different story. Because now seeing 4 heads and to flip them, okay, 4 times and see heads, then the probability would have been 1/2 times 1/2 times 1/2 times 1/2. So all of these are independent. So this is, the probability, okay, on the first, multiplied by the probability on your second, multiplied by the probability on your third flip, and then multiplied by the probability on the fourth flip, and then of seeing those heads. So as you can see, so this answer would have been 1 over 2 to the power of 4, okay, which is, I guess, just 1 over 16, right, which is 2 times 2 times 2 times 2. But, okay, if you have seen all of these already, and now you're just interested in, okay, well, on the next flip, what's the probability? Then that probability is 1/2, okay, which is much different than it is trying to see 4 heads in a row. All right, so that's the independence. So here, the independence is past results don't really, okay, are a prediction of the future results. They're kind of independent in a coin flip. And you would see the same thing in rolling a die, right? So let's say if we would roll a die once, that roll, whatever we get, is not going to have any dependence, okay, on the future rolls that we do. So every time we pick, okay, a die and we toss it, we always have 1 in 6 chance of, seeing a 1, a 2, a 3, a 4, a 5, or a 6. And then once we do that roll and we pick it up again, we're back to the same exact probabilities or odds to see that. Because past, okay, is independent from the future in these cases, right? So you also see this not just with the repetition of the same kind of event that you want to see. So flipping a coin, for instance, okay, or sorry, seeing a heads, you might have events which are 2 different events, okay? And if they're completely different, so let's say if they were, like flipping a coin and then rolling a die, right? And you can do those simultaneously. You can flip the coin and roll the die at the same time. And, you can ask the question, all right, so what's the probability of seeing a heads and then, maybe seeing a 3 on your result? Well, seeing a 3 has nothing to do with, seeing a heads on your actual coin. So those 2 events, okay, let's say that they were, event A and maybe event B. So the event A could have been, okay, flipping a coin, and event B is going to be seeing a 3, okay, on rolling a die. So those 2 are independent. And when they are independent, then the way that we calculate the probabilities, so for instance, in this case, the A, which could be defined as, seeing a heads, and then the B, okay, would have been defined as, maybe seeing a 3 on a die. Those 2 events are completely independent of each other. So in that case, you can just literally take the probability of A happening. So in this case, it would have been, okay, so the probability of A is 1/2, because that is true. And then you just simply multiply it by the probability of seeing that 3, which in this case would have been 1/6, okay, for that die. And then when you multiply the 2, so the multiplication of the 2 would give you the resultant, so in this case 1/12, and you can change that to percents if you like, of the overall probability, right? So this would have been the probability of A and B occurring. So that's what you would have. So the independence allows us to pretty much kind of use multiplicative kind of principle, except with respect to probabilities. But really, this is just the probability of independent events kind of principle that we have. Now, if you had more than 2 events, let's say if you had 3 events and all of them were independent, or 4 events, and so on, then all you do is you just multiply the probabilities to be able to get the overall probability of all of those events happening at the same time, right? And we kind of did see this, except we were doing it with exactly the same thing. So in terms of the rolling the heads, right? So this right here, we had 4, okay, events. On the first flip, we wanted to see a heads. On the second flip, we wanted to see a heads, third and fourth. And then all we did was we just multiplied them through, right? And we could have drawn a tree diagram and then, counted it all up in terms of theoretical probabilities and found the same thing. But those are independent, right? So past and future were independent of each other, although they were dealing with the same coin, flipping. And here, if you have even different events, you can do exactly the same thing. All right, so let's show, maybe another example where this kind of can come about, and you can see that, these 2 events are going to be independent of each other. So let's say the probability of a computer crash, right? Let's say we wanted to turn our computer and it crashes, is 0.1%. And then the probability of a car not starting on a given day is 0.08%. All right? So our computer that we have has nothing to do with the car. So those 2 events are going to be independent. So, having a crash is independent of the car not starting. And therefore, we can now start to compute the probabilities when they're independent of each other by just simply multiplication. So if you wanted to know what the probability of a computer crash and let's say your car not starting say on the same day, for instance, okay, if that was the case, you would just multiply the two and you would find out that the probability would be tiny because of the fact, okay, that these probabilities are small. Okay, and now, so here's another question that could be asked. You can turn probabilities into odds, which are, a very similar thing. Okay, if you've forgotten about odds, I'll put up a link up above there. You can go back and refresh yourself on how to find those odds, okay, from probabilities. So here it says, find the odds in favor of a car starting and our computer not crushing. All right. So what we have, the way that it's given, so really, if I would call event A the computer crash, okay, so really what I'm trying to find is, not the computer crash, because I want to make sure that the computer is not crashing. All right, so the probability of this, so that's the complement. So I know that this would have been actually, so this is going to be 99.9%, which is just 100% minus 0.1. All right, or I can write this as decimal notation like this. And then I have the second one, so let's say the car not starting, so that would have been B. Okay, so event B is 0.08%. And what I'm looking for is, I do want our car to start. Okay, so I also want the opposite. So that would have been, and again, I can write 100%, minus 0.08%. Okay, so this is going to be 99.92%, or simply 0.9992 if I wanted to turn it into decimal. Now, they're asking me for the odds, okay, in favor, okay, of our car starting and our computer not crashing. So the probability, okay, of not A and not B, well, in this case, so because these two are independent, I can just take and multiply these together. So that's going to give me the probability. So that is 0.999. When you're doing the multiplication, do turn it into decimal or a fraction. All right, so this is what we would have. Now this is going to be, so let's pop out the calculator here. So 0.999 multiplied by 0.9992. Okay, so I'll keep the whole thing. So 9982008. So that's the probability, all right, of those two. So highly unlikely. Now, if I want to know the odds, so if you remember, odds, okay, are going to be, so probability of A and B, okay, and this is going to be, so in favor, so we want these to be in favor, 2, okay, the complement of this, so that's going to be the complement, I'll put it in brackets, is going to be 1 minus the probability, okay, so the complement right here, so that's that, okay, and then I can find the odds exactly within here. So, so here was, okay, so this is going to be 1 minus the answer here. So 1, whoops, equals, so that's our answer. All right, that's clear. Hopefully it's going to remember. 1 minus, no, it didn't. Okay, so 0.9982008. So that's going to be, a very tiny amount. 992. This one is 0.9982008. Now, we don't like to have the odds like this, and don't forget that you can write the odds kind of in a fraction form so that it also reduces it for us. So this is going to be, the minus the complement, so here on the other side. All right, so let me write that out. So I'm going to divide those two out, okay? 0.998208 divided by 0.0017992. equals, and so there we have it. This is going to be about, I'm going to kind of round this, so 555, okay, all over 1, or simply the odds, okay, are very much so in our favor. All right, so that would have been calculating the odds within, okay? So these are two independent events. So the key thing out of this video is the fact that you have to kind of keep in mind are two events or more than two events completely independent of each other. They don't have an impact. So once the occurrence of one has no impact on the occurrence of another event at all. And if that's the case, then to find the probabilities of both of those things happening, all you have to do is just multiply the individual probabilities, okay? This is not the case when they are dependent on each other, but I'll talk about that in a different video. All right, so I hope that you found this useful. It's kind of an introduction to this concept of independent events and then finding the probabilities, okay? And we'll see you in a future video. Bye, everybody.